Okay, so let me dive into some administrative points first. So again, recall that assignment 1 is due next Wednesday. You have about 150 hours left, and I use hours because there's a more imminent sense of doom. And remember that a third of those hours you'll be unconscious, so you don't have that much time. It's really running out. And you might think that you have late days and so on, but these assignments just get harder over time, so you want to save those and so on. So start now. Let's see, so there's no office hours or anything like that on Monday. I'll hold makeup office hours on Wednesday because I want you guys to be able to talk to me about especially projects and so on. So I'll be moving my office hours from Monday to Wednesday. Usually I have my office hours at 6 p.m. Instead, I'll have them at 5 p.m. And usually it's in gates 260, but now I'll be in gates 259. So -1 on both. And yeah. And also to note, when you're going to be studying for midterm that's coming up in a few weeks, make sure you go through the lecture notes as well, which are really part of this class. And I kind of pick and choose some of the things that I think are most valuable to present in a lecture, but there's quite a bit of more material to be aware of that might pop up in the midterm, even though I'm covering some of the most important stuff usually in the lecture. So do read through those lecture notes. They're complementary to the lectures. And so the material for the midterm will be drawn from both the lectures and the notes. Okay. So having said all that, we're going to dive into the material. So where we are right now, just as a reminder, we have the score function. We've looked at several loss functions, such as the SVM loss function last time. And we looked at the full loss that you achieve for any particular set of weights over your training data. And this loss is made up of two components. There's a data loss and a regularization loss, right? And really what we want to do is we want to derive now the gradient expression of the loss function with respect to the weights. And we want to do this so that we can actually perform the optimization process. And in the optimization process, we're doing a gradient descent, where we iterate evaluating the gradient on your weights, doing a parameter update, and just repeating this over and over again so that we're converging to the low points of that loss function. And when we arrive at a low loss, that's equivalent to making good predictions over our training data in terms of the scores that come out. Now, we also saw that there are two kind of ways to evaluate the gradient. There's a numerical gradient, and this is very easy to write, but it's extremely slow to evaluate. And there's an analytic gradient, which you obtain by using calculus, and we'll be going into that in this lecture quite a bit more. And so it's fast, exact, which is great, but it's not, you can get it wrong sometimes. And so we always perform what we call gradient check, where we write all the expressions to compute the analytic gradient, and then we double check its correctness with numerical gradient. And so I'm not sure if you're going to see that. You're going to see that definitely in the assignments. Okay, so now you might be tempted to, when you see this setup, we just want to derive the gradient of the loss function with respect to the weights. You might be tempted to just write out the full loss and just start to take the gradients as you see in your calculus class. But the point I'd like to make is that you should think much more of this in terms of computational graphs instead of just thinking of one giant expression that you're going to derive with pen and paper, the expression for the gradient. And the reason for that, so here we're thinking about these values flowing through a computational graph where you have these operations along circles, and they're basically little function pieces that transform your inputs all the way to the loss function at the end. So we start off with our data and our parameters as inputs. They feed through this computational graph, which is just all these series of functions along the way. And at the end, we get a single number, which is the loss. And the reason that I'd like you to think about it this way is that these expressions right now look very small, and you might be able to derive these gradients. But these expressions in computational graphs are about to get very big. And so, for example, convolutional neural networks will have hundreds, maybe, or dozens of operations. So we'll have all these images flowing through like pretty big computational graph to get our loss. And so it becomes impractical to just write out these expressions. And convolutional networks are not even the worst of it. Once you actually start to, for example, do something called a neural Turing machine, which is a paper from DeepMind, where this is basically a differentiable Turing machine. So the whole thing is differentiable. The whole procedure that the computer is performing on a tape is made smooth, and is differentiable computer, basically. And the computational graph of this is huge. And not only is this is not it, because what you end up doing, and we'll go into recurrent neural networks in a bit, but what you end up doing is you end up enrolling this graph. So think about this graph copied many hundreds of time steps. And so you end up with this giant monster of hundreds of thousands of nodes and little computational units. And so it's impossible to write out, here's the loss for the neural Turing machine. It's just impossible. It would take like billions of pages. And so we have to think about this more in terms of data structures of little functions transforming intermediate variables to get us the loss at the variant. Okay? So we're going to be looking specifically at computational graphs and how we can derive the gradient on the inputs with respect to the loss function at the variant. Okay? So let's start off simple and concrete. So let's consider a very small computational graph where we have 3 scalars as an input to this graph, x, y, and z, and they take on these specific values in this example of -2, 5, and -4. And we have this very small graph or circuit. You'll hear me refer to these interchangeably, either as a graph or a circuit. So we have this graph that at the end gives us this output -12. Okay? So here what I've done is I've already pre-filled what we'll call the forward pass of this graph, where I set the inputs and then I compute the outputs. Okay? And now what we'd like to do is we'd like to derive the gradients of the expression on the inputs. And so what we'll do now is I'll introduce this intermediate variable q after the plus gate. So there's a plus gate and a times gate, as I'll refer to them. And this plus gate is computing this output q. And so q is this intermediate as a result of x plus y, and then f is a multiplication of q and z. And what I've written out here is basically what we want is the gradients, the derivatives df by dx, df by dy, df by dz. And I've written out the intermediate, these little gradients for every one of these 2 expressions separately. So now we've performed the forward pass going from left to right. And what we'll do now is we'll derive the backward pass. We'll go from the back to the front, computing gradients of all the intermediates in our circuit, until at the very end we're going to be left with the gradients on the inputs. And so we start off at the very right. And as a base case sort of this recursive procedure, we're considering the gradient of f with respect to f. So this is just the identity function. So what is the derivative of just identity mapping? What is the gradient of df by df? It's 1, right? So the identity has a gradient of 1. So that's our base case. We start off with a 1. And now we're going to go backwards through this graph. So we want the gradient of f with respect to z. So what is that in this computational graph?
X plus y.
Okay, it's q. So we have that written out right here. And what is q in this particular example? It's 3, right? So the gradient on z, according to this, will become just 3. So I'm going to be writing the gradients under the lines in red, and the values are in green above the lines. So we have the gradient in the front is 1, and now the gradient on z is 3. And what red 3 is telling you really intuitively, keep in mind the interpretation of a gradient, is what that's saying is that the influence of z on the final value is positive and with sort of a force of 3. So if I increment z by a small amount h, then the output of the circuit will react by increasing, because it's a positive 3, will increase by 3h. So a small change will result in a positive change on the output. Now the gradient on q in this case will be, so df by dq is z. What is z? -4. Okay? So we get a gradient of -4 on that path of the circuit. And what that's saying is that if q were to increase, then the output of the circuit will decrease. Okay? If you increase by h, the output of the circuit will decrease by 4h. That's the slope, is -4. Okay. Now we're going to continue this recursive process through this plus gate. And this is where things get slightly interesting, I suppose. So we'd like to compute the gradient on f on y with respect to y. And so the gradient on y with this, in this particular graph will become, let's just guess and then we'll see how this gets derived properly. So I hear some murmurs of the right answer. It will be -4. So let's see how. So there are many ways to derive it at this point because the expression is very small and you can kind of glance at it. But the way I'd like you to think about this is by applying chain rule. Okay. So the chain rule says that if you like to derive the gradient of f on y, then it's equal to df by dq times dq by dy, right? And so we've computed both of those expressions. In particular, dq by dy we know is -4. So that's the effect of the influence of q on f. Is df by dq, which is -4. And now we know we'd like to know the local influence of y on q. And that local influence of y on q is 1, because that's the local, as I'll refer to as the local derivative of y for the plus gate. And so the chain rule tells us that the correct thing to do to chain these two gradients, the local gradient of y on q and the kind of global gradient of q on the output of the circuit, is to multiply them. So we'll get -4 times 1. And so this is kind of the crux of how backpropagation works. This is very important to understand here, that we have these two pieces that we keep multiplying through when we perform this chain rule. We have q computed x plus y, and the derivative on x and y with respect to that single expression is 1 and 1. So keep in mind the interpretation of the gradient. What that's saying is that x and y have a positive influence on q with a slope of 1. So increasing x by h will increase q by h. Okay? And now what we eventually like is we'd like the influence of y on the final output of the circuit. And so the way this ends up working is you take the influence of y on q, and we know the influence of q on the final loss, which is what we are recursively computing here through this graph. And the correct thing to do is to multiply them. So we end up with -4 times 1, okay, -4. And so the way this works out is basically what this is saying is that the influence of y on the final output of the circuit is -4. So increasing y should decrease the output of the circuit by -4 times the little change that you've made. And the way that ends up working out is y has a positive influence on q. So increasing y slightly increases q, which slightly decreases the output of the circuit. Okay? So chain rule is kind of giving us this correspondence. Go ahead.
In practice, would you store it in sort of like in a variable format or in a symbol format, or would you store it in terms of what the other variables are?
Yeah, thank you. So we're going to get into this. You'll see basically this entire class is about this. So you'll see many instantiations of this, and I'll drill this into you by the end of this class, and you'll understand it. You will not have any symbolic expressions anywhere once we compute this, once we're actually implementing this, and you'll see implementations of it later in this. It will always be just vectors and numbers, raw vectors and numbers. Okay, and looking at x, we have a very similar thing that happens. We want df by dx, that's our final objective, and we have to combine it. We know what is x's influence on q, and what is q's influence on the end of the circuit. And so that ends up being the chain rule. So you take -4 times 1 and gives you -1. Okay? So the way this works, to generalize a bit from this example, and the way to think about it is as follows. You are a gate embedded in a circuit, and this is a very large computational graph or circuit. And you receive some inputs, some particular numbers, x and y, come in, and you perform some operation f on them and compute some output z. Okay? And now this value of z goes into computational graph, and something happens to it. But you're just a gate hanging out in a circuit, and you're not sure what happens. But by the end of the circuit, the loss gets computed. Okay? And that's the forward pass. And then we're proceeding recursively in the reverse order backwards. But before that, actually, before I get to that part, right away when I get x and y, the thing I'd like to point out that during the forward pass, if you're this gate and you get your values x and y, you compute your output z. And there's another thing you can compute right away, and that is the local gradients on x and y. So I can compute those right away because I'm just a gate and I know what I'm performing, like say addition or multiplication. So I know the influence that x and y have on my output value. So I can compute those guys right away. Okay? But then what happens near the end, so the loss gets computed, and now we're going backwards. I'll eventually learn about what is my influence on the final output of the circuit, the loss. So I'll learn what is dl by dz in there. The gradient will flow into me. And what I have to do is I have to chain that gradient through this recursive case. So I have to make sure to chain the gradient through my operation that I performed. And it turns out that the correct thing to do here by chain rule, really what it's saying, is the correct thing to do is to multiply your local gradient with that gradient. And that actually gives you the dl by dx. That gives you the influence of x on the final output of the circuit. So really, chain rule is just this added multiplication where we take our, what I'll call global gradient of this gate on the output, and we chain it through the local gradient. And the same thing goes for y. So it's just a multiplication of that guy, that gradient by your local gradient if you're a gate. And then remember that these x's and y's, they are coming from different gates, right? So you end up with recursing this process through the entire computational circuit. And so these gates just basically communicate to each other the influence on the final loss. So they tell each other, okay, if this is a positive gradient, that means you're positively influencing the loss. And if it's a negative gradient, you're negatively influencing the loss. And these just gets all multiplied through the circuit by these local gradients. And you end up with, and this process is called backpropagation. It's a way of computing through a recursive application of chain rule through computational graph the influence of every single intermediate value in that graph on the final loss function. And so we'll see many examples of this throughout this lecture. I'll go into a specific example that is slightly larger, and we'll work through it in detail. But I don't know if there are any questions at this point that anyone would like to ask. Go ahead.
What happens if Z is used by 2 other nodes?
If Z is used by multiple nodes, I'm going to come back to that. You add the gradients. The correct thing to do is to add them. So if Z is being influenced in multiple places in the circuit, the backward flows will add. But we'll come back to that point. Good?
What happens if you have like a bunch of inputs to F, 100, 1,000, and the way you randomly initialize your weights, you end up that because your squashing function, the value at F is somewhere on the asymptote. So then when you're computing the gradient, the change in any one of the components will not really change the function output that much. Aren't you?
Yeah. So I think I would have repeated your question, but you're jumping ahead like 100 slides. So we're going to get to all of those issues, and we're going to see, you're going to get what we call vanishing gradient problems and so on. We'll see. Okay? Let's go through another example to make this more concrete. So here we have another circuit. It happens to be computing a little two-dimensional sigmoid neuron, but for now, don't worry about that interpretation. Just think of this as that's an expression. So 1 over 1 plus e to the whatever. So the number of inputs here is 5, and we're computing that function, and we have a single output over there. Okay? And I translated that mathematical expression into this computational graph form. So we have to recursively, from inside out, compute this expression. So we first do all the little w times x's, and then we add them all up, and then we take a negative of it, and then we exponentiate that, and then we add 1, and then we finally divide, and we get the result of the expression. And so what we're going to do now is we're going to backpropagate through this expression. We're going to compute what the influence of every single input value is on the output of this expression. What is the gradient here? Yeah, go ahead.
Is it accustomed to use functions like plus or times as binary functions instead of multiple parity functions?
So for now, you're concerned about the interpretation of plus maybe in these circles. For now, let's just assume that this plus is just a binary plus. It's a binary plus gate. And we have there a +1 gate. I'm making up these gates kind of on spot. And we'll see that what is a gate or is not a gate is kind of up to you. I'll come back to this point in a bit. So for now, we have several more gates that we're using throughout. And so I just like to write out, as we go through this example, several of these derivatives. So we have exponentiation. And we know for every little local gate what these local gradients are, right? So we can derive that using calculus. So e to the x derivative is e to the x, and so on. So these are all the operations, and also addition and multiplication, which I'm assuming that you have memorized in terms of what the gradients look like. So we're going to start off at the end of the circuit, and I've already filled in a 1.00 in the back, because that's how we always start this recursion, with a 1.0, right? Since that's the gradient on the identity function. Now we're going to backpropagate through this 1 over x operation, okay? So the derivative of 1 over x, the local gradient, is negative 1 over x squared. So that 1 over x gate, during the forward pass, received input 1.37, and right away that 1 over x gate could have computed what the local gradient was. The local gradient was negative 1 over x squared. And now during backpropagation, it has to, by chain rule, multiply that local gradient by the gradient of it on the final output of the circuit, which is easy because it happens to be at the end. So what ends up being the expression for the backpropagated gradient here from the 1 over x gate? The chain rule always has two pieces. Local gradient times the gradient from the top or from above. So that's correct. So we get minus 1 over x squared, which is the gradient df by dx. So that is the local gradient, negative 1 over 3.7 squared. And then multiplied by 1.0, which is the gradient from above, which is really just 1 because we've just started. And so I'm applying chain rule right away here, and the output is negative 0.53. So that's the gradient on that piece of the wire where this value was flowing. Okay, so it has a negative effect on the output. And you might expect that, right? Because if you were to increase this value, and then it goes through a gate of 1 over x, then if you increase this, then 1 over x gets smaller. So that's why you're seeing negative gradient, right? So we're going to continue backpropagation here. the next gate in the circuit, it's adding a constant of 1. So the local gradient, if you look at adding a constant to a value, the gradient on x is just 1, right, by basic calculus. And so the chained gradient here that we continue along the wire will be, we have local gradient, which is 1, times the gradient from above the gate, which it has just learned is negative 0.53, okay? So negative 0.53 continues along the wire unchanged. And intuitively, that makes sense, right? Because this value floats, and it has some influence on the final circuit. And now if you're adding 1, then its influence, its rate of change, its slope towards the final value doesn't change. If you increase this by some amount, the effect at the end will be the same. Because the rate of change doesn't change through the +1 gate. It's just a constant offset. Okay, we continue derivation here. So the gradient of e to the x is e to the x. So to continue backpropagation, we're going to perform, so this gate saw input of negative 1. It right away could have computed its local gradient. And now it knows that the gradient from above is negative 0.53. So to continue backpropagation here and applying chain rule, we would receive, okay. So these are mostly rhetorical questions, I'm not sure. but yeah, basically, e to the negative 1, which is e to the x input to this x gate, times the chain rule, right? So the gradient from above is negative 0.53, so we keep multiplying that on. So what is the effect on me, and what do I have an effect on the final end of the circuit? Those are being always multiplied. So we get negative 0.2 at this point. So now we have a times negative 1 gate. So what ends up what happens to the gradient when you do a times negative 1 in the computational graph? It flips around, right? Because we have basically a constant multiply of input, which happened to be a constant of negative 1. So negative 1 times negative 1 gave us negative 1 in the forward pass. And so now we have to multiply by a, that's the local gradient, times the gradient from above, which is 0.2. So we end up with just positive 0.2 now. So we're now continuing backpropagation. We're backpropagating plus. And this plus operation has multiple inputs here. The gradient, the local gradient for the plus gate is 1 and 1. So what ends up happening to what gradients flow along the output wires? So the plus gate has a local gradient on all of its inputs always will be just 1, right? Because if you just have a function, x plus y, then for that function, the gradient on either x or y is just 1. And so what you end up getting is just 1 times 0.2. And so, in fact, for a plus gate, always you see the same effect where the local gradient on all of its inputs is 1. And so whatever gradient it gets from above, it just always distributes gradient equally to all of its inputs, because in a chain rule, they'll get multiplied. And when you multiply by 1, something remains unchanged. So a plus gate is kind of like a gradient distributor, where if something flows in from the top, it will just spread out all the gradients equally to all of its children. And so we've already received one of the inputs is gradient 0.2 here on the very final output of the circuit. And so this influence has been computed through a series of applications of chain rule along the way. So now there was another plus gate that I've skipped over. And so this 0.2 kind of distributes to both 0.2 equally. So we've already done a plus gate. And there's a multiply gate there. And so now we're going to backpropagate through that multiply operation. And so the local gradient, so what will be the gradients for W0 and X0? What will be the gradient for W0 specifically? Did someone say 0? 0 will be wrong. It will be, so the gradient W1 will be, W0, sorry, will be negative 1 times 0.2. Good. And the gradient on X0 will be, there's a bug, by the way, in the slide that I just noticed like a few minutes before I actually created the class. It started the class. So you see 0.39 there, it should be 0.4. It's because of a bug in the visualization, because I'm truncating at 2 decimal digits. Anyways, but basically that should be 0.4, because the way you get that is 2 times 0.2 gives you 0.4, just like I've written out over there. So that's what the output should be there. Okay, so we've backpropagated this circuit here, and we've backpropagated through this expression. And so you might imagine in our actual downstream applications, we'll have data and all the parameters as inputs. The loss function is at the top, at the end. So we'll do forward pass to evaluate the loss function, and then we'll backpropagate through every piece of computation we've done along the way, and we'll backpropagate through every gate to get our inputs. And backpropagate just means apply chain rule many, many times. And we'll see how that is implemented in a bit. Sorry, did you have a question?
No, just W1 and X1.
Oh yeah, so I'm going to skip that because it's the same. So I'm going to skip the other times gate. Any other questions at this point?
So this process takes on the order of the same time it takes to forward propagate.
That's right. So the cost of forward and backward propagation is roughly equal.
Is it actually within like a constant? Do you know what the constant is?
Well, it should be. It almost always ends up being basically equal when you look at timings. Usually the backward pass is slightly slower. But yeah. Okay, so let's see. One thing I wanted to point out before we move on is that the setting of these gates, like these gates are arbitrary. So one thing I could have done, for example, is some of you may know this. I can collapse these gates into one gate if I wanted to. For example, there's something called the sigmoid function, which has that particular form. So sigma of x, which is the sigmoid function, computes 1 over 1 plus e to the minus x. And so I could have rewritten that expression, and I could have collapsed all of those gates that made up the sigmoid gate into a single sigmoid gate. And so there's a sigmoid gate here, and I could have done that in a single go, sort of. And what I would have had to do if I wanted to have that gate is I need to compute an expression for how this, so what is the local gradient for the sigmoid gate, basically. So what is the gradient on the sigmoid gate on its input? And I have to go through some math, which I'm not going to go into detail, but you end up with that expression over there. It ends up being 1 minus sigmoid of x times sigmoid of x. That's the local gradient. And that allows me to now put this piece into a computational graph. Because once I know how to compute the local gradient, everything else is defined just through chain rule and multiplying everything together. So we can backpropagate through this sigmoid gate now. And the way that would look like is the input to the sigmoid gate was 1.0. That's what went into the sigmoid gate. And 0.73 went out. So 0.73 is sigma of x. Okay, and now we want the local gradient, which is, as we've seen from the math that I performed there, 1 minus sigma of x times sigma of x. So you get sigma of x is 0.73, multiplying 1 minus 0.73. That's the local gradient. And then times, well, we happen to be at the end of the circuit, so times 1.0, which I'm not even writing. So we end up with 0.2. And of course, we get the same answer, 0.2, as we received before, 0.2, because calculus works. But basically, we could have broken up this expression down and did one piece at a time, or we could just have a single sigmoid gate. And that's kind of up to us at what level of hierarchy do we break these expressions. And so you'd like to intuitively cluster these expressions into single gates if it's very efficient or easy to derive the local gradients, because then those become your pieces.
Do libraries typically do that, where they notice, oh, hey, that's a sigmoid, I know how to do that fast?
Yes. So the question is, do libraries typically do that? Do they worry about what's easy to or convenient to compute? And the answer is yeah, I would say so. So if you notice that there's some piece of operation you'd like to do over and over again, and it has a very simple local gradient, then that's something very appealing to actually create a single unit out of. And we'll see some of those examples actually in a bit, I think. Okay. I'd like to also point out that the reason I like to think about these computational graphs is it really helps your intuition to think about how gradients flow in a neural network. It's not just, you don't want this to be a black box to you. You want to understand intuitively how this happens. And you start to develop, after a while of looking at computational graphs, intuitions about how these gradients flow. And this, by the way, helps you debug some issues, like, say, we'll go to vanishing gradient problem. It's much easier to understand exactly what's going wrong in your optimization if you understand how gradients flow in networks. It will help you debug these networks much more efficiently. And so some intuitions, for example, we already saw that the add gate, it has a local gradient of 1 to all of its inputs. So it's just a gradient distributor. That's like a nice way to think about it. Whenever you have a plus operation anywhere in your score function or your comnet or anywhere else, it just distributes gradients equally. The max gate is instead a gradient router. And the way this works is, if you look at the expression, like we have, great, these markers don't work. So if we have a very simple binary expression of max of xy, so if this is a gate, then the gradient on x and y, if you think about it, the gradient on the larger one of your inputs, whichever one was larger, the gradient on that guy is 1, and the smaller one has a gradient of 0. And intuitively, that's because if one of these was smaller, then wiggling it has no effect on the output because the other guy is larger, and that's what ends up propagating through the gate. So you end up with a gradient of 1 on the larger one of the inputs. And so that's why max gate is a gradient router. If I'm a max gate and I have received several inputs, one of them was largest of all of them, and that's the value that I propagated through the circuit. At backpropagation time, I'm just going to receive my gradient from above, and I'm going to route it to whoever was my largest input. So it's a gradient router. And the multiply gate is a gradient switcher. I actually don't think that's a very good way to look at it. But I'm referring to the fact that it's not actually, never mind about that part. Go ahead.
What happens if for one of your max gates, its two inputs are equal? What happens to the backward?
So yeah, so your question is what happens if the two inputs are equal when you go through max gate? Yeah, what happens?
Probably goes to one of them arbitrarily, whichever one you encounter.
Yeah, you pick one. Yeah. Yeah, I don't think it's correct to distribute it to all of them. I think you'd have to pick one. Yeah, but that basically never happens in actual practice. Okay, so max gradient here. Actually, I have an example. So Z here was larger than W, so only Z has an influence on the output of this max gate, right? So when 2 flows into the max gate, it gets routed to Z, and W gets a 0 gradient because its effect on the circuit is nothing. There's 0. Because when you change it, it doesn't matter when you change it because Z is the larger value going through the computational graph. I have another note that is related to backpropagation, which we already addressed through a question. I just wanted to briefly point out with a terribly bad-looking figure that if you have these circuits and sometimes you have a value that branches out into a circuit and is used in multiple parts of the circuit, the correct thing to do by multivariate chain rule is to actually add up the contributions at the operation. So gradients add when they backpropagate backwards through the circuit. If they ever flow, they add up in this backward flow. All right, we're going to go into implementation very soon. I'll just take some more questions.
Is there a closed loop case instead of open loop?
Thank you for the question. The question is there ever like loop in these graphs? There will never be loops. So there are never any loops. You might think that if you use a recurrent neural network that there are loops in there, but there's actually no loops because what we'll do is we will take a recurrent neural network and we'll unfold it through time steps, and this will all become, there will never be a loop in the unfolded graph where we've copy-pasted that small recurrent net piece over time. You'll see that more when we actually get into it. But these are always DAGs. There's no loops. Okay, awesome. So let's look at implementation and how this is actually implemented in practice, and I think it will help make this more concrete as well. So we always have these graphs, computational graphs. These are the best way to think about structuring neural networks. And so what we end up with is all these gates that we're going to see in a bit. But on top of the gates, there's something that needs to maintain connectivity structure of this entire graph. What gates are connected to each other? And so usually that's handled by a graph or a net object, usually a net. And the net object has these two main pieces, which is the forward and the backward piece. And this is just pseudocode, so this won't run. But basically, roughly the idea is that in the forward pass, we're iterating over all the gates in the circuit, and they're sorted in topological order. What that means is that all the inputs must come to every node before the output can be consumed. So these are just ordered from left to right. And we're just forwarding. We're calling a forward on every single gate along the way. So we iterate over that graph, and we just call forward on every single piece. And this net object will just make sure that that happens in the proper connectivity pattern. In the backward pass, we're going in the exact reversed order, and we're calling backward on every single gate. And these gates will end up communicating gradients to each other, and they all get chained up and computing the analytic gradient at the back. So really, a net object is a very thin wrapper around all these gates, or as we'll see, they're called layers. Layers or gates, I'm going to use those interchangeably. And they're just very thin wrappers around connectivity structure of these gates and calling a forward and a backward function on them. And then let's look at a specific example of one of the gates and how this might be implemented. And this is not just a pseudocode, this is actually a more like correct implementation in some sense, like this might run at the end. So let's consider a multiply gate and how it could be implemented. A multiply gate in this case is just a binary multiply, so it receives two inputs, x and y. It computes their multiplication, z is x times y, and it returns z. And all these gates must basically satisfy this API of a forward call and a backward call. How do you behave in a forward pass, and how do you behave in a backward pass? And in a forward pass, we just compute whatever. In a backward pass, we eventually end up learning about what is our gradient on the final loss. So dl by dz is what we learn. That's represented in this variable dz. And right now, everything here is just scalars. So x, y, z are numbers here. dz is also a number telling you the influence on the end of the circuit. And what this gate is in charge of in this backward pass is performing the little piece of chain rule. So what we have to compute is how do you chain this gradient dz into your inputs x and y. In other words, we have to compute dx and dy. And we have to return those in the backward pass. And then the computational graph will make sure that these get routed properly to all the other gates. And if there are any edges that add up, the computational graph might add all those gradients together. Okay, so how would we implement the dx and dy? So for example, what is dx in this case? What would it be equal to, the implementation? Y times dz, great. And so y times dz. Additional point to make here, by the way, note that I've added some lines in the forward pass. We have to remember these values, x and y, because we end up using them in the backward pass. So I'm assigning them to a self dot, because I need to remember what x, y are, because I need access to them in my backward pass. In general, in backpropagation, and when we build these, when you actually do the forward pass, every single gate must remember the inputs and any kind of intermediate calculations that it has performed that it needs to do, that it needs access to in the backward pass. So basically, when we end up running these networks at runtime, just always keep in mind that as you're doing this forward pass, a huge amount of stuff gets cached in your memory. And that all has to stick around, because during backpropagation, you might need access to some of those variables. And so your memory ends up ballooning up during the forward pass. And then in backward pass, it gets all consumed. And we need all those intermediates to actually compute the proper backward pass. So that's...
You can do a forward pass if you're not going to do a backward pass fast. Like a lot faster.
Yeah, so if you know you don't want to do backward pass, then you can get rid of many of these things and you don't have to compute, you don't need to cache them. So you can save on memory, for sure. But I don't think most implementations actually worry about that. I don't think there's a lot of logic that deals with that. Usually we end up remembering it anyway.
Well, it does seem like if you want to test on your validation set, that's way faster than just doing one pass through your training.
I see. Yeah, so I think if you're in an embedded device, for example, and you worry really about your memory constraints, this is something that you might take advantage of. If you know that a neural network only has to run in test time, then you might want to make sure to go into the code and make sure nothing gets cached in case you want to do a backward pass. Questions? Yes?
If we are computing the local gradients during the forward pass, then we don't need to remember the other variables.
You're saying if we remember the local gradients in the forward pass, then we don't have to remember the other intermediates? I think that might only be the case in some simple expressions like this one. I'm not actually sure if that's true in general. But I mean, you're in charge of, remember whatever you need to perform the backward pass on a gate-by-gate basis. You can remember whatever you feel like has lower footprint and so on, and you can be clever with that. Okay, so just to give you guys an example of what this looks like in practice, we're going to look at specific examples, say in Torch. Torch is a deep learning framework, which we might go into a bit near the end of the class, that some of you might end up using for your projects. If you go into the GitHub repo for Torch and you look at, like basically, it's just a giant collection of these layer objects. And these are the gates. Layers, gates, the same thing. So there's all these layers. That's really what a deep learning framework is. It's just a whole bunch of layers and a very thin computational graph thing that keeps track of all the layer connectivity. And so really, the image to have in mind is all these things are your Lego blocks. And then we're building up these computational graphs out of your Lego blocks, out of the layers. You're putting them together in various ways depending on what you want to achieve. And so you end up building all kinds of stuff. Right? So that's how you work with neural networks. So every library is just a whole set of layers that you might want to compute. And every layer is just implementing a small function piece. And that function piece knows how to do a forward and it knows how to do a backward. So just with a specific example, let's look at the mol constant layer in Torch. The mol constant layer performs just a scaling by a scalar. So it takes some tensor x. So this is not just a scalar, but it's actually like an array of numbers, basically. Because when we actually work with these, we do a lot of vectorized operations. So we receive a tensor, which is really just a n-dimensional array, and we scale it by a constant. And you can see that this layer actually just has 40 lines. There's some initialization stuff. This is Lua, by the way, if this is looking some foreign to you. But there's initialization, where you actually pass in that A that you want to use as your scaling. And then during the forward pass, which they call update output, in a forward pass, all they do is they just multiply AX and return it. And in the backward pass, which they call update grad input, there's an if statement here. But really, when you look at these 3 lines that are most important, you can see that all it's doing is it's copying into a variable grad input, which it needs to compute. That's your gradient that you're passing up. The grad input is, you're copying grad output. Grad output is your gradient on the final loss. You're copying that over into grad input, and you're multiplying by the scalar, which is what you should be doing, because your local gradient is just A, and so you take the output you take the gradient from above, and you just scale it by A, which is what these 3 lines are doing. And that's your grad input, and that's what you return. So that's one of the hundreds of layers that are in Torch. We can also look at